Welcome. My name is Jerzy Forchurts and I'm a product manager on GKE. With me on the virtual stage, Joel Mayer, Chief Architect at OpenX, and Ivan Gusev, Principal Infrastructure Architect at OpenX. In the next 25 minutes, we will show you how OpenX looks at performance and cost, how to become a hero metering and understanding your utilization on GKE, how to optimize for what you need, and then what does it mean in practice. So let's get started. When we talk about cost to performance optimization on GKE, we mention the two dimensions for a reason. While the ultimate amount of your spend on the infrastructure depends on the provisioned resources, it is important to understand your application, how it operates, and what you expect from the service it represents. So is your application stateless or stateful? Is it serving or data processing? How long does it take to start from deployment to active? And how much time does it need to drain? So the second factor, expected SLO of service you are providing. What is the latency of the service that you expect? Can you afford longer startup time if this means lower cost? Do you need to provision for high availability? How does it impact the choice of machine types and the level of over provisioning? So how do you do this in practice? Let's hear the live story from Joel and Ivan from OpenX.
Thanks, Jerzy. So these numbers represent OpenX in a nutshell prior to our migration. We were 100 billion requests per day. We're running 15 million lines of code, deployed on 15,000 servers around the globe in 5 different regions. Now, OpenX is an ad exchange, and so those billions of ad requests are coming from a multitude of clients with an SLA of between 150 to 400 milliseconds, depending on the client. And we call this set of services that handle those requests the delivery system, and that comprises about half of our infrastructure cost. So as you can see from the load balancer stats on the screen, we have both a daily pattern with peaks and troughs, and then a weekly pattern as well with lower traffic on weekends and then higher during the week. Prior to migration, we had a pretty traditional deployment strategy. Services were packaged as RPMs, and they were deployed via salt stack on physical hardware. But we felt that being on-prem was limiting our efficiency. So when we moved to the cloud, our goal was to modernize for the purposes of gaining efficiency, scalability, and consistency. And we felt that Kubernetes was the right answer for that, but we also knew we didn't want to be running Kubernetes ourselves. So when we evaluated the different offerings from the competitors, it seemed like GKE was probably about 2 years ahead of everybody else, both in terms of features and stability. Now, early on, Ivan had looked at the CPU utilization of all of our services, both at peak and on average, to get a sense of how much compute we'd actually need in the cloud. And what he found was pretty interesting. So the x-axis here is peak utilization, and the y-axis is average utilization. Now, in an on-prem environment, your server count's fixed, so unless your service is running at full tilt all day long, off-peak is basically wasted compute. And with our diurnal traffic pattern and our weekend patterns, we had a lot of wasted compute. The graph also illustrated for us that we could save significantly on compute cost if we could buy only what we needed throughout the day and could share hardware with auxiliary services. Now, keep in mind, this is only one dimension of CPU utilization. We're not looking at memory or I/O. Those aren't captured either. And that's why some of the numbers may look a little sad. So the services circled there, those are the delivery system. And we knew that these were the candidates for GKE and that moving to GKE would enable us to scale compute based on our traffic patterns and needs, and also to gain efficiency by optimal packing of the services on hardware. Let's take a brief look at some of the before and after. So on-prem, services were rarely restarted. You would deploy and you would start, and it would run unless there was a problem. Also, they didn't grow and shrink in number. Whereas in the cloud, the pods were very dynamic, spinning up, spinning down, and also the cluster size was dynamic, growing or shrinking. So we're going from a very static environment to a very dynamic environment. And that's what we wanted, but it also introduced some challenges for us. A few other differences worth noting. On-prem hardware is dedicated to a service. And as a result, that service was tuned for maximum utilization of that server. Whereas in the cloud, you're optimizing your pod for the resources that you've allocated to it. And then you're optimizing your cluster for overall utilization. So what that means, practically speaking, is we weren't just migrating from one containerized environment to another. We were moving from a very server-based model to a completely unoptimized container model. And that added a lot of complexity. But what it did mean is that we could go from using the fewest servers possible at peak to a world where we could provision only what we needed at any given time. And that was our definition of victory. So we had an idea of what was technically possible in Kubernetes, but we still needed to translate that into a cost model. And to accomplish that, Yvonne did some pretty extensive modeling. There were a couple dimensions to that. First, he modeled the type of compute that we would use. Would we be using on-demand? Or could we benefit from a commitment and use committed use? Or, most cost-effectively, could we use preemptible nodes? Second, he translated compute to hosted services in some cases. Rather than running React KV on PVMs, we decided, let's take advantage of Bigtable. Let's take advantage of LB, of load balancing. And finally, he adjusted the amount based on our actual utilization. So that model gave us a good idea of what we could get to. Actually, getting to that target efficiency is the journey that we'd like to share with you.
Before we go on the journey of autoscaling, let's recap what we're dealing with. In Kubernetes, there are two layers of abstraction: the workload layer, where you deploy your pods, and the cluster layer, where you deal with nodes. Google Kubernetes Engine provides automation at both of these layers so that your service works optimally all the time. The horizontal pod autoscaler, or HPA, is adding and removing pods of the same time based on the utilization metrics, which can be CPU utilization or custom metrics like requests per second or number of tasks in a PubSub queue. This solves for the cases where more requests call for more machines, which would be likely the case of your serving frontend, application backend, or pool of processing workers. But what if the amount of memory or CPU is not appropriate for your process, or your system cannot scale by adding more machines easily? Take a database or file system as an example. This is where vertical pod autoscaler comes to rescue. It is monitoring the resource utilization and allows for adjusting the pod requests to either improve performance or reduce unused resources. Similarly, on the infrastructure layer, Cluster Autoscaler automatically adds and removes nodes in the cluster. This operation happens in response to pending pod requests by the scheduler and CPU utilization of the node. Node auto-provisioning decides on the type of node pools on your behalf automatically. This way, Cluster Autoscaler can always keep the most optimal, meaning cheapest, configuration of your cluster. So, in summary, GKE is offering 4 dimensions of autoscaling to help you optimize cost and performance of your workloads. So, how did OpenX use them to optimize for cost?
Thank you, Jersey. Glad to be here. Horizontal pod autoscalers allow each deployment to scale independently while maintaining each pod workload at nearly constant rate. This significantly reduces the number of performance scenarios that need to be tested and optimized for. We found that for most workloads, CPU utilization targets work best as changes in code often change execution efficiency and would need to be constantly adjusted if a custom metric is used. As a global company, we also observed regional differences in the code execution path. This can significantly complicate application rating for particular workload volumes. Custom metrics are still useful if your workload is not CPU bound, but rather I/O or network bound. Remember, Kubernetes does not give you explicit choice over pod deletion process. When deployment is scaled down, Kubernetes observes pod disruption budget while randomly selecting a pod to scale down. This creates imbalance in utilization of nodes. Cluster Autoscaler normally takes care of underutilized nodes. If you need an additional control, you can use the scheduler, an open source project helping to balance resource utilization of nodes. When a cluster has one or more pods pending, the cluster autoscaler kicks in and determines what node pools can and should increase in size to accommodate these workloads. To choose the best option, it considers fitness of each node configuration to accommodate pending pods. In other words, how well particular node size will match pods that need to be scheduled. It also takes into account an estimated cost of cluster size increase and will attempt to increase multiple node pools sequentially should some kind of fault or stockout event be detected. At OpenX, we started with very prescriptive model when we defined exactly what node pool will host each workload. However, that often meant that there is only one application per node. One application pod per node. When we allowed the cluster autoscaler to choose the best node pool dynamically, we found that provisioned virtual machines match our workloads much more closely, which use less memory and less CPU. We waste less. GKE also offers fast scale-down cluster autoscaler profile, which removes underutilized nodes much more rapidly, thus lowering the cost of your cluster faster. Joel, back to you.
Thanks, Ivan. So Ivan just described the benefits of the horizontal pod autoscaler and the cluster autoscaling. Once we had implemented both of those, our compute usage began to follow our traffic patterns, both the diurnal daily pattern and the weekly pattern, which you can see on the slide there. That's the beauty of autoscaling. When it's enabled at the application layer and at the hardware layer, it translates into cost efficiency. Let's take a brief side journey to talk about measurement. So optimization without measurement is nearly impossible. You need visibility into your starting point and where your resources are being consumed. So you need the ability to measure improvement. You want to understand your pod utilization. How are they performing? You want to understand your node utilization. How many are being used and to what extent? You also need to understand your overall cost, because at the end of the day, that's what matters. So really, you'd love to measure everything. And we used a combination of different tools to accomplish that. First, we used Prometheus and Grafana to measure service metrics and application metrics. All our services were instrumented, and Kubernetes offers those metrics out of the box as well. Then we also used BigQuery to track the cost metrics that GCP makes available. And there's an entire separate talk on that topic, which we encourage you to check out. And then finally, we used the GKE metering dashboard to see which services were consuming the most resources and cost. When it comes to optimization, your destination is the model you've created, and measurement is your GPS. It tells you how far you've come and also how far you've got to go. Let's talk about some of the next stops on our optimization journey.
Sure. With HPA and cluster autoscaling configured, we next looked at pod optimization. For the average case, pod tuning is a matter of making sure you understand ratio of RAM and CPU needed for the application to operate at certain throughput. Then you just set requests and limits accordingly. In some cases, you may also need to tune underlying technology, like JVM if needed. If your pod isn't utilizing the requested resources, you can reduce the request, which will release the capacity back to the cluster. If your pod consistently overutilizing the requested resources, then you may need to increase requests in order to improve service continuity. Have you seen out-of-memory killer in action? GKE provides vertical pod autoscaler that watches your pod resource utilization and recommends pod sizes. It is an automated way of process that we used at OpenX.
Vertical pod autoscaling does three things. It watches the resource usage by the selected pods. After it collects enough data, it provides recommendations to what should be the actual resource that should be specified in the pod spec. And then, if enabled, it applies the recommendation to selected pods. You can apply the recommendations yourself, similarly to what OpenX did with their workloads. You can also enable automatic actuation of your pods according to the recommendations. This can happen in two ways: at pod creation time or continuously.
The VPA recommendations that Jersey just described are incredibly useful. And another GKE feature that enabled us to optimize performance was CPU Manager, which Ivan is going to tell us a little bit more about.
Sure. Just like the noisy neighbor effect on virtual machines, a similar effect exists for pods. Sometimes that's by design to achieve overall higher virtual machine utilization. However, OpenX runs a large number of applications written in Erlang, and Erlang Virtual Machine has its own schedule of threads, which work most efficiently if they run on the same CPU core all the time and aren't swapped out or competing for CPU with other applications. For scenarios like this, Kubernetes has a feature called CPU Manager. It provides additional guarantees of CPU allocation on top of what Kubernetes resource requests are already doing. While resource requests are only used by Kubernetes scheduler to make informed decisions on where to schedule pods, the CPU manager enforces CPU allocation to the pod, continuously prohibiting all other pods from stepping into CPU managed pod territory and minimizing the number of context switches. The flip side of CPU Manager is that pod cannot exceed their requests and efficiently sandboxed in terms of CPU capacity. For our Erlang systems, that's exactly what we wanted. Joel?
So with auto-scaling enabled and our pods tuned, we still needed to tackle another area of optimization. How do we make the most use of a cluster that has a diverse set of services running in it? So in a nutshell, how do we optimally bin pack? There are two parts to that challenge. One, how do we size our pods so that they're more easily accessible? And then two, how do we size our nodes so that they can accommodate the right number of pods? We have some control over both dimensions, so we needed to find a sweet spot.
Kubernetes scheduler takes several pods properties into consideration to make decision on what node pod gets scheduled. Two primary capacity-related fields are resource requests for CPU and memory. Kubernetes scheduler does not scale cluster up or down, but rather works with available nodes, aiming to fit as many pods as possible into provisioned capacity. And when this is not possible and pods are pending, cluster autoscaler provisions more nodes. Here's an example of CPU and memory constrained nodes. On the left graph, you can see that even though only 78% of CPU capacity is allocated, no pods larger than 4 CPUs can be scheduled. Similarly, on high CPU node scheduler cannot add any new pods because the single pod has already allocated pretty much all memory capacity. So we ended up with CPU resource utilization of just 28%. How can this bin packing efficiency, can it be improved? You can make all pods equal size and make sure that each node can fit exactly n pods. This is not always ideal, as workload capacity requirements and ability to scale vertically differ a lot. At OpenX, we use 2 to the power of n rule. We standardize pod sizes on 1, 2, 4, and 16 cores. This also matches GCE standard VM sizes and allows us to move between different VM sizes without a need to optimize pod sizes again. While doing so, make sure that you account for space reserved by Kubernetes for daemon sets and kernel. Also, don't forget to pay attention to your sidecar and init containers, as their resource requests might be affecting scheduling decisions. Generally speaking, you will get best results of bin packing when pod requests are small fractions of CPUs, while nodes are relatively large. Yet, if you're using preemptible virtual machines, you have to watch for losing large number of pods in case of preemption. Measuring bin packing efficiency is quite simple, as you need to aggregate all workload resource requests and divide it by total capacity. It can be tracked as a cluster-wide metric or node pool-specific ratio. We observed that auto-scaled clusters with no pod size optimizations, we usually get around 75% of CPU reserved, while clusters with improved bin packing efficiency reach all the way to 95%. Similar optimizations can be done for memory dimension. However, memory generally requires significant headroom and usage is less predictable compared to CPU cores. Our memory reservations are currently measured at around 50%. Optimization of bin packing is in more than one dimension is totally possible, but depending on your workload profile, it may end up exponentially harder to implement with every new dimension that you add. We decided to leave this exercise for the future. Joel?
Ivan. So early on, when we were doing our cloud cost modeling, Ivan picked out services that could take advantage of preemptible virtual machines. And for the delivery stack, we assumed that roughly 70% of our compute could be preemptible. Now, when we first tested, we were discouraged because it was hard to get the PVM capacity we needed. But after discussing with the GCE team, they encouraged us to try a smaller sized PVM node. After making that change, we were much more successful in finding the PVM capacity, and we've even exceeded our initial target PVM utilization. But it is another factor to consider in bin packing. So the GKE cluster autoscaler allows us to tap into different PVM pools by attempting to scale up different node pools sequentially. That could be node pools of different VM sizes or using different compute families. So while we've presented our journey as a nice linear progression, the reality was a bit more winding with some back and forth between the different optimization techniques. That being said, the 6 approaches we've discussed are all worth looking into. First, configure and tune your horizontal pod autoscalers. 2, enable the cluster autoscaler. 3, right-size your pod requests and/or use the vertical pod autoscaler. Number 4, use the CPU manager for the applications that need that level of guarantee. Number 5, optimize your bin packing. And then number 6, find the right machine type for your workload. So thanks to the work that Ivan and the team have done, we're now able to run our GKE clusters on a very small set of node pools that scale based on price and availability. And thanks to the optimized pods, the HPAs, the right choices in machine sizes, we've improved efficiency by over 45%. One of the things that was invaluable to the success of this project was the ability to meet with and ask questions of the different teams whose technology we're using, whether that was Jersey and the GKE Autoscalers team, the CPU manager team, the GCE team, or any one of the other teams that we met with. We were really impressed by their willingness to work with us and help us use their technology. We also took advantage of the GCP PSO team to help us in various parts of the migration and found their help to be very valuable as well. Thank you particularly to Will Beebe. So Jersey, thanks for allowing us to share some of our story here with you. And to the audience, good luck with your own optimization efforts. Jersey, back to you.
Thank you, Joel and Ivan, for sharing your experience with us. For those of you willing to get on a journey of optimizing cost to performance on GKE, we just published 2 solution guides that will get you an advice on best practices of running cost-effective Kubernetes applications and how to use node auto-provisioning to optimize your resources. These guides are a collective summary of experiences of OpenX and many other companies who shared their stories with us. We will keep updating it as we add more functionality to Google Kubernetes Engine. You should also take a look at related breakout sessions airing this week. On behalf of Google Cloud team, I want to thank you for watching.